There are additional electrophilic aromatic substitution reactions that you would need to know. These you don't have to know the mechanism for. For example, I can add iodine to the benzene. We studied the reaction where we can add the halogen to the benzene, either a chlorine or a bromine. We can add iodine this way. The catalyst that we use for the reaction is not and FeI3, pay attention with iodine. With iodine, we normally use copper with it. So we use copper chloride as a catalyst. These two are going to react with each other and make the electrophile I plus. You don't have to know the mechanism of the reaction here. So this mechanism you are not responsible for. All what you are responsible for is to generate your electrophile, and then the electrophile immediately is going to undergo electrophilic aromatic substitution, and it's going to replace the hydrogen on the benzene by the iodine, and this is the way to get iodobenzene. Another reaction that comes in handy in synthesis, we can, you already know this reaction here, we can sulfonate, add the sulfonic acid on the benzene. Now, once we add the sulfonic acid on the benzene, we know that the sulfonic acid is an electron withdrawing group. So it's going to direct the meta position. So we can add whatever we want to group on the meta position, and then we can wash the sulfonic acid away. We can wash it away by two ways. Either we can use water in presence of an acid. And if you use water in presence of acid and heat, you're going to wash the sulfonic acid away and you are going to get a hydrogen instead. So you're going to go back to the benzene. This comes in handy if you want to add groups on the meta position. And then you don't want any other groups on the benzene other than the groups on the meta position, then you can add your sulfonate. You can add the groups on the meta position, and then you can wash the sulfonic acid away. You get your benzene. This is one way. Another way is if you add water in presence of a base. So this is water in presence of an acid. This is water in presence of a base. If you're adding water in presence of a base, then in this case you are substituting the sulfonic acid with the OH. The mechanism here goes by a nucleophilic substitution, but you are not responsible for this mechanism. All what you're responsible for is the reagent and the reaction itself. So over here, I will form a phenol, and this is one way to make phenols. You start with benzene sulfonic acid, you add water in presence of a base. Another reaction that comes in handy is the nitrization reaction. This reaction you're not responsible for the mechanism for. You're only responsible for the reaction itself and the product that comes out of it. It comes in handy because I can replace the NH2 group on the benzene by any of the groups that you see over here. And these groups vary in direction. So OH, we know that it directs the ortho and the para. It's a strong activating group. Iodine in there, fluorine, chlorine, bromine, all of those, they direct the ortho and the para. Cyanide directs the meta position. So it's really important to know this reaction. Now, this reaction happens whenever I start with aniline. So aniline is a must. And we know to get aniline, we need to start with benzene. So starting with benzene, okay, and we go ahead and, actually I missed a step. So we start with benzene and we do nitration, HNO3 in presence of H2SO4. Then in this case, we are going to get the nitro group on the benzene. Now, once we get the nitro group on the benzene, we can easily reduce the nitro group by using any of the reducing agents that we've talked about before. So we can use either iron in presence of an acid, we can use zinc in presence of an acid. In there, we can use hydrogen in presence of PT. So any of those reducing agents, we are doing reduction. And we said that the mechanism for this reaction you're not responsible for, and we will get the aniline. Once you get the aniline, then you are going to add this reagent to it. This is sodium nitrite in presence of an acid at a very cold temperature that is going to react with the amino group on the benzene. The NH2 group is going to change into an N2 group. We call this a group over here, it's called a diazonium group. So N2 on the benzene is called a diazonium group. So this whole thing now is called a benzene diazonium ion. N2 is an excellent leaving group. So it's going to leave by nucleophilic aromatic substitution with any of those reagents. So if you want to replace the N2 with OH, you add water. If you want to replace it with iodine, you add Ki. This is another way of making iodobenzene. So this is the first way of making iodobenzene. This is the second way of making iodobenzene. If you want to introduce a fluorine, this is the way to do that. You do HBF4 in presence of heat. All of these reagents you are responsible to know. If you want to add a chlorine, a bromine, other than using a bromine in presence of FeBr3, then you can use copper bromide or copper chloride. Adding a cyanide, this is a way to add a cyanide stat. Let's say, for example, if we needed just a benzene, there are two ways to do it. Either by washing away the sulfonic acid, we can get rid of the benzene, or we can do the diazonium ion, and then we can add the H3PO2. Then we're going to get the benzene. This handout that I posted on eCampus, I'd like you to look at it. It does have the summary of the reactions that we've been talking about in this chapter. The activating and deactivating table, this one is not complete because it does not show the classification of the meta directors. Use the other table that I posted in there. This section over here is important because it tells you how we can change the functional group and change the directing effect. This is very useful in synthesis whenever we are doing synthesis. So if you're doing synthesis, you can simply change an electron withdrawing group to an electron donating group by doing reduction. We have other reagents we said for reduction. You can use iron in presence of an acid or zinc in presence of an acid. In this reaction, also, we can do reduction and change using either Wolff-Kishner or Clemenson from a meta director to an orthopera director. These are really important when you're doing synthesis because sometimes you need a group that is orthopera directing, but you are starting with a meta director. So all what you need to do is just simply do reduction if that group that you're starting with has a carbonyl in it. If you are starting with an orthopera director in R on the benzene that has a benzylic hydrogen, you can simply do oxidation in there. And then you're going to end up getting your acid that is a meta director that we've been talking about in this chapter. You're not allowed to have the sheet in the exam. Just look at it for studying. So back to this question over here, synthesis is an important section in organic. And whenever you are given synthesis, you will be given a reactant and you will be given a product. And you will be asked to design a method in order to go from the reactants to the products. Normally what we do, we look at the products and then compare it to the reactants. We go backward. This is called retrosynthesis, just to see what did we add. So over here, we added an acid. We changed the CH3 into an acid. We know that in order to get a carboxylic acid, this is the result of an oxidation of a benzylic carbon that has a hydrogen on the benzene. So if we're starting with a benzylic carbon that has a benzylic hydrogen, we can simply do oxidation with KMnO4 in presence of a base or water, and we can oxidize that carbon into a carboxylic acid. Carboxylic acids, these are meta directors. in there. And the CH3 is an orthopara director. So you got to pay attention over here when you look at your product and see that your substituents in your product, they are orthopara to each other. This means that I cannot oxidize the CH3 before adding the NO2 first. Okay, so it makes sense over here that I'm starting with a CH3. I need to do nitration, introduce the nitro group on the benzene in the ortho position and the para position. But since the product here has only the para is going to be major, so you can say isolate. So you choose just the product that you need. Here I need the para, which is going to be always the major. Para is always the major. So you choose the one that you need. You don't have to worry about the other isomer. So the ortho product to just discard, choose the one that you need and carry on the synthesis. Para, and then after you make your para, now you can oxidize by either KMNO4 in presence of a base or water. Any oxidizing agent can do the job. Review this oxidation reaction in there, and you're going to end up getting your carboxylic acid from the CH3. Same idea, the moment I see an acid in my product, this means that that acid came from a CH3. However, now see, I have my substituents, they are meta to each other. This means that I am oxidizing the CH3 and I am making that CH3 an acid, and then I'm doing the nitration because I know that this acid directs the meta position. Here I'm having a bromine and NO2. To know which one to add first, look at the direction in there. Bromine is an orthopara director. Nitro is a meta director. Since they are meta to each other, then I'm starting to add the nitro first by nitration and then do the bromination in there. Okay, always look at your product and work from your product to your reactant. Again, this is called retrosynthesis. So I have my nitro is a meta director and the acid is a meta director. I know that both they direct the meta position, but they are para with respect to each other, or para with respect to each other. So this means that I should have an electron donating a group in there to direct the nitro to the para position, and then I can oxidize the R group into a carboxylic acid. So I'm going to start first by introducing the CH3 or any R group on the benzene. Any R group can do the job because I can oxidize that R group into a carboxylic acid. The arrangement in there. So I'm using here the simplest alkyl halide with AlCl3. Do Friedel-Crafts. Friedel-Crafts happens because there is no electron withdrawing group on the benzene. So this one is going to happen. I'm going to make my toluene. So you have your toluene in there. The moment you make your toluene, this is an ortho-para director. Do the nitration and get your nitro on the para position. You will have the ortho isomer, but you can neglect that. Okay, you can simply isolate, neglect that, and then you can do the oxidation of the CH3 and turn it into a carboxylic acid. Here I am adding an R group and a bromine. The bromine is an orthopara director, and the R group over here is an orthopara director as well, but both of them are meta with respect to each other. So this is going to tell me that this R group over here is added by Friedel-Crafts acylation. So there was a carbonyl in there that was a meta director to direct the bromine, and then you can reduce that carbonyl into a CH2 by Clemmensen reaction. So we're going to start by adding the R group by Friedel-Crafts acylation in there. Count the carbons that you need. This is 1, 2, and 3. So add those up. Make sure that you have an acyl group in there. We're not doing Friedel-Crafts alkylation. We're doing Friedel-Crafts acylation. You're introducing an electron with a drawing group on the benzene that directs the meta position. You are doing the bromination, form the bromine on the meta position, and then you are doing the Clemenson or Wolff-Kishner, whatever that is, to reduce the carbonyl into a CH2. I didn't add any carbons here. All I did is just a reduction of the carbonyl into a CH2. When you have a product that has a lot of bramines, assuming the both ortho and para position, then think that you will have over here and on this position over here, you should have a strong electron donating group. Like for example, an NH2, this is the easiest one. Stay away from the OH. Always do NH2 because NH2 reaction, I can simply use that, do the diazonium ion, and then get rid of the N2 by simply adding a hydrogen in there. So always start with the NH2. Forget about the OH. So the first step is going to be nitration. I'm going to nitrate. I'm going to reduce into an NH2. So once you have the NH2 in there, this is a strong electron donating group. So it's going to direct the ortho and the para, and it's going to direct both ortho positions and the para positions at the same time. Just as a side note, we have mentioned this before. NH2 is a strong electron donating group. If it was present alone, then if you are doing the bromination or the nitration, this is FeBr3, then all positions are going to be brominated at the same time. So you're going to end up having 3 bromines in this case, ortho and para to the NH2. If I want to limit the reactivity of the NH2, you go ahead and you introduce an strong electron with a drawing group on the benzene. So this is the NH2, and you have like a strong one like NO2, for example. Then in this case, you will limit the reactivity. If you have a bromine in presence of FeBr3, then you're going to end up here the para position is occupied. Then the NH2 is only going to brominate the ortho position. So you're going to end up getting the ortho position over here brominated. Let's say if the NO2 is on the meta, then in this case, the NH2 is going to form the ortho and the para separate. Okay, ortho and para, but the ortho will not be formed because of static hindrance, so it's just going to form the para product. If you have a moderate electron with a drawing group, then that moderate electron with a drawing group will allow the dibromination. So put that in there. We've talked about this before. Here you go. So this is the so if you have a moderate electron with a drawing group, then you're going to end up having the dibromination in there. So no groups at all on the benzene or a moderate deactivating group, then you're going to end up having dibromination. The only way you can limit the bromination, the amount of the bromination, is to introduce a strong electron with a drawing group on the benzene. So here we're going to brominate all the positions. And now it's time to get rid of the NH2 in there. So in the product, I don't have it. So if you don't have it, then this is the way to go. You use the sodium nitrite in presence of HCl, 0 degrees. You are responsible to know the condition for the reaction. You are you are changing the NH2 into a diazonium ion, and then you're going to use the H3PO2 that is going to replace the N2 with a hydrogen from this acid. I wanted to include this reaction over here. This is called an intramolecular Friedel-Crafts acylation. Intra means you have your reagent and your starting material within the same molecule. So here my starting material is the benzene, and my reagent is the acyl chloride. And notice that they are both in the same molecule. The mechanism is going to proceed exactly the same. So you got to understand what you're doing over here. We said that You're going to start with your reagent. Your reagent, you're going to add it to your catalyst, and you're going to form the electrophile. So go ahead and start. It's exactly as you were doing before, but before the acyl chloride was separate from the benzene. Here it's connected to the benzene. If it is connected, this means that the product is going to be a cycle once the electrophile is formed. So you are going to end up having a Lewis acid, a Lewis base over here, Lewis acid on the aluminum, make your complex in there. This is going to leave, you make your acylium ion as we used to do. This is going to be your electrophile. So once you have your electrophile, then it's going to come and attack the benzene by the two steps that we already know. Double bond is going to open up, pick up your electrophile. For these types of reactions, please number your carbons. It really makes a difference in there to know, because if I start numbering over here, I would know that I'm going to end up having a cycle of 6 carbons. So this is why over here the cycle is going to close and you're going to have 6 carbons in there. Double bond's going to open up. So this means that I am forming a bond between this carbon over here and this carbonyl over there. And this is the new bond that I formed. Numbering the carbons the same way, it's going to be 1, 2, 3, 4, this is 5, and this is 6. Put your carbonyl on carbon number 6 so that you won't forget that. And then the last step is for the base, comes, takes the hydrogen, form a double bond, and you're going to restore the aromaticity of the ring.